We spoke about inertial trajectories, and we linked them to straightness. We said that, of course, if somebody's in an accelerated frame and you see an inertial particle moving, then you might see it with all kinds of jagged and curved motion and so on and so forth. But obviously, we don't judge things from accelerated frames. We go into an inertial frame, then we look at another particle and we say, okay, it has a straight line trajectory. Then if it had a curved trajectory, of course, it couldn't be inertial. So could we take that as a good mapping, like inertia and straightness? Is that anybody?
That sounds reasonable.
Sounds reasonable. Can you think of some objections? Try to destroy that hypothesis. Okay, can it map uniquely, one-to-one, unambiguously? So I'll give you, for example, one. There's several objections. One is that a stationary particle is inertial and it's just a dot. A dot is not a straight line. It's not straight. It doesn't have the geometric characteristic of straightness. So if a dot can represent the trajectory of a stationary particle, then we can't uniquely say that something has to have a straight line trajectory in order to be inertial. Okay, so I wouldn't map straightness to inertia. There are other objections. Can you think of something else? For example, you can have a linearly accelerated particle. The particle can accelerate along a line. It can even go back and forth, stop for a while, go here, go back. Each individual motion was a straight line, right? From here to here, from here to here, from here to here. Add them all up together, it makes one big straight line. And if you just drew a straight line like this, you would have no conception whatsoever what this particle was doing. In fact, it might not even need to be a particle. You draw a straight line on a graph, and it could just be the straight edge of an object. Also, there's so much information that's lost, obviously. We have no idea which direction it's traveling, right? If it's a straight line. Did it move this way? Did it move that way? Even if it was inertial. We have no idea of the speed. So there's a lot of things missing. There's an inertial particle that can be stationary, right, which is a dot. So the dot line objection can trouble us why we have to represent inertial trajectories in two different ways, and that's something we would like to overcome. We know, of course, from Galilean inertia, the indistinguishability, we can't really say that an inertial particle is stationary or moving, right? They're just moving relative to each other. So one person's dot is another person's straight line, another inertial system's straight line. So really we shouldn't distinguish between a dot and a straight line. So that any inertial particle's trajectory that is a straight line will be seen as a dot in its own rest frame. So there are many reasons why you would not map inertia and straightness. Now, somehow intuitively we think of straight and inertia, and I'm going to tell you that one could in fact map them well. And there is a hint in the very notion that we have of a trajectory being a straight line, because after all, if you think about it, the clue is in the very concept of a trajectory as a straight line. Because when you see a particle moving, do you see a straight line? Does anybody ever see a particle move and see actually a straight line? What happens is that your brain adds up all the individual perceptions, kind of like time-lapse photography, and turns it into a straight line. You don't see a straight line. Now, does that give anybody a clue? What is added into the picture by our brain? I kind of gave it away when I said time-lapse photography. We're adding in time. So in other words, if we add time into the diagram, as opposed to just a spatial diagram of a trajectory, we can overcome everything. Imagine that you have let's say I'll make the t-axis vertical, even though usually you see it horizontal, because in relativity that's the way we usually do it. So we're going to have, and I'm not talking about relativity yet, we have a t-axis, we have an x-axis. Okay, as time passes, it's going to be a straight line. How would you represent uniformly moving particles of different speeds? And the slope, or the inverse of the slope, if I have t this way and x that way, is going to be the speed. So every speed will be represented by a straight line at a different angle. So first of all, that's very, very nice, because we now can distinguish between inertial particle speeds as opposed to a trajectory line, which if we're just moving along the x, all of those would just be one straight line along the x. What about a stationary particle? Well, a stationary particle has a particular x value, wherever it is, here, let's say. As time goes by, it maintains that x value. So simply a straight line, we might as well start from the 0 point of the x, right, where the x and the t axes meet, and we'll make it along this line. In other words, a stationary particle effectively can be considered as having a straight line along the t-axis. Now, since any inertial particle, even if it's like this, in its own frame, will consider itself to be stationary, so every inertial particle really can represent itself like that in the diagram. Okay? But any other inertial frame will see it with some relative speed. So it's really not really relevant what angle we put, but it's nice that we can represent an inertial state as just a line along the t-axis, for example. That kind of, it's just a cute way of reminding ourselves what all these different things that we mentioned now. Now, if I draw this line, can it be the straight edge of an object? No, because what this represents is this location at this time, this location at this time, this location at this time. That's what this line, which is a set of points, each of these points represents a particular location at a particular time, a particular location at a particular time. So it represents all these locations at very specific times. So now we can see that we've overcome all the objections that we had before. We said that an inertial particle that's stationary has a dot shape as opposed to a straight line, even though you couldn't really distinguish one between the other. But here we find that we add time in, and we have the space-time diagram, that stationary and inertially moving, uniformly moving, have the same representation, a straight line. We also see that only an inertial object, or stationary object, or a dynamic object, an object in motion and uniformly moving, can be represented this way. It can't be that this line represents just some straight edge of an object. And also we find that we have all this additional information. We know the direction that it's moving. It's moving along at time 0 for me. It was here, at time 1 it was here, at time 2 it was here. As opposed to if it was moving the other direction, we would have to have a line slanted in that direction, because it was moving at time 1 it was here, at time 2 it was here. And we know the speed. So it's a really, really nice, unique, unambiguous one-to-one mapping. Straightness and inertia, but we are required to have a tx axis. And it could be curved, of course, if it's accelerated, but if it's inertial, it's going to be a straight line. A law of inertia, which we can now phrase as inertial particles have straight lines in this space-time diagram. Now, we want to use this very nice model to now model what we learned about gravity. We learned in the first lecture that, so I think it's pretty intuitive that, let's take a simple case where they're moving alongside each other, two inertial particles moving the same speed and direction near each other, right? I think it's pretty clear that if the particles have a relative acceleration, that lines have to curve towards each other, away from each other, and so on. There's no way that you can get two straight lines. You can have, again, you can have a line like this and a line like that. That's just simply relative inertial motion, relative constant speed. But in order to have relative acceleration for this separation to actually accelerate as time goes on, they're going to have to curve towards each other, away from each other. Okay? Here you have two that are curving towards each other. Here you have two that are curving away from each other. So we would say, okay, let's say we have this time and we have space and this diagram. Inertial particles have, let's say this is a straight line, and maybe it went along this axis, so here it was very distant from any galaxies, no gravitational interaction, and then suddenly it starts more and more and more coming into a region where the gravitational effects will become important, right? So in terms of the line, as time goes on, it's getting into that region. So, and even in the region where gravity is important, in this place at these times, it'll be inertial, so it'll be a straight line. Which is good, because we said that an inertial particle is inertial, even in the presence of matter, even where Newtonian physics says there's a strong gravitational field. But what we need is two neighboring inertial particles. So we'll take another inertial particle. It could be moving at the same speed, but just slightly displaced. So it starts out, one is over here on the x-axis at time 0, one is over here at the time at time t is equal to 0, right? So they're very near each other in space, right? A small distance between them. And this is moving with a certain speed, and this is moving with the same speed. So they're always maintaining the same distance between them. Two neighboring particles moving along parallel, straight line inertial trajectories. So now they're reaching more and more into the region where gravity, Newtonian gravity, is strong and definitely felt. So now they're reaching more and more into the region where gravity, Newtonian gravity, is strong and definitely felt, right? They're passing planets where people are teaching that, oh, gravitational acceleration, here it's uniform, it's 9.8, or a different planet, who knows what it is, right? So there's definitely gravity all over the place. So will that show up here? Will this diagram be exactly the same? Is that what Einstein is saying? What do you think? Does that work? Shouldn't there be some indication? Shouldn't you be able to tell from the diagram that gravity is working? So the answer is, well, what do we need to tell? What we need to see is a relative acceleration. We need to be able to look at this diagram and with the correct way of interpreting it to realize that there is relative acceleration. So now we take an additional step and we say, since it's so nice, let's assume that there really is something in nature that corresponds to this combination, space, time. That there really is this physical aspect of the universe, that space-time, a combination of space and time. And what it means is that we have this law. Right? In order to make that a little bit more mathematical, a straight line in ordinary space, right, is very intuitive to us. We know what that is and we know how to define it and so on. A straight line in a space-time diagram is a little bit more abstract. It's not a line in actual physical space. Of course, we draw it in physical space on a diagram, but the diagram represents something different than regular physical space. It's space-time, so it's a little bit more abstract. Now, straightness, we have an intuitive notion of what it would mean to be straight in this space-time diagram, and therefore, if we say that the universe has space-time, space and time combined in some way, we can imagine that it has this geometric structure that allows there to be straightness in space-time. It's not completely obvious, right? We have straightness in space, but we say there could be, as we see, straightness in space-time, and what it is inertia. And if we want to recognize that it's a little bit more abstract than just ordinary, a flat piece of just anywhere in space, a straight line. So we call it a geodesic. That's the technical term for a straight line. Even the straight line that we ordinarily draw along a flat piece of paper is a geodesic. It's a geodesic of that flat piece of paper. Okay, so we have inertial lines in this diagram are geodesics of space-time. And we'll also now give a terminology. If we have space-time, then a line in that space-time, any line in that space-time, will be called a world line. Just historically, a world line meaning it's the history forever of any particle, and you can draw all the particles. So it's like the history of the world, so to speak, with all the time in it. So it's a world line. A world line is simply one of those lines. It represents where a particle was when. So now we have a very nice phrasing of the law of inertia. Inertial particles have geodesic world lines. That's a really nice, concise summary of everything that we said. Inertial world lines are geodesics of spacetime. Okay, and that encapsulates everything, all the different things that we spoke about. And so we really believe now that there's a combination of space and time that is real, because we're going to require some kind of physical specification that inertial particles should have geodesic world lines, geodesics of spacetime. Gravity is not about particles accelerating, as one thinks about it in ordinary physics and Newtonian physics. In fact, what gravity is about is inertia. Inertial particles, when encountering a region where there is matter, they're all still inertial. Just they experience a relative acceleration. Now, we thought of the medium before space, and now we understand the medium of spacetime. It has an effect on the medium, spacetime, such that although inertial particles remain inertial, they experience a relative acceleration. So now we would say, okay, we had a very beautiful model of what inertia is, right? Inertial world lines are geodesics of spacetime. Can we now use this model for a region where there's gravity? And here we have two inertial particles, parallel, straight, geodesic world lines. All right? Right? And there's relative acceleration between the particles. So now, there goes our model. Right? I mean, this is certainly not geodesic. Right? If these lines curve towards each other, away from each other, they're not geodesic. So, although we have a very nice model for real inertial particles, in other words, in the absence of gravity, where the absence of gravity really means where no measuring instrument of ours can ever detect anything that we can attribute to gravity, because really there is gravity everywhere. But so no gravity means we can't detect it. So there we're satisfied with our law of inertia. Inertial particles have geodesic world lines, geodesics of spacetime. But that only works, like I said, when you can't notice any gravitational effects, because once you are in the region where gravitational effects are experienced, namely, what does a gravitational effect means? Relative acceleration of these inertial particles, then your model fails. Of course, Einstein said, no, I'm not giving up my model. So, well, how do you, I mean, this is definitely so. And you can see that mathematically, you can see that intuitively. So what Einstein said is, I like my model, I don't care. If this happens, then that's what's going to happen. So you say, well, then they're not geodesics. He says, no. They are inertial, and they are therefore geodesics. Both of these are geodesics. And you laugh, you say, well. You say, no, space-time is warped. Your diagram is a diagram of Tx for space-time when it's not warped, when you can't feel any gravitational effects. It's simply not applicable to regions of spacetime where the effect that we call gravity can be measured. How do you draw it? You can't really draw it. You can do it mathematically. And I'm going to define, you say, well, what do you mean it's warped? I say, well, I'm defining warped. Warped spacetime is such that it has geodesics, just like unwarped spacetime has. It has geodesics. The notion of geodesity, of straightness, can be defined in it. And I'm just saying that. I'm taking that as given. And it also has the property that despite the fact that these are geodesics, there will be this, and we call it deviation of the geodesics, which translates, of course, into, if this is a map of space-time, then it translates into relative acceleration of neighboring inertial particles. And you'll say, well, you're just kind of, we had an objection, and you're just saying, well, the question that we asked is really the answer. Say, yeah, that's right. We had a problem. How do we map geodesics that deviate? So I'll say, well, I'll just define a space called a warped spacetime. And what I mean by warped is exactly this, that although it has geodesics, the geodesics experience geodesic deviation, the type that we mentioned. So, well, then becomes a mathematical problem. Can you do that? Can you define such a space? Can you define such a space? And amazingly enough, you can. And surprisingly enough, or maybe some people, of course, in physics say it's not surprising, it's trivial. It turns out that curvature of surfaces in ordinary space gives us exactly the right mathematics for this moment. That's not to say space-time is curved like a surface, and nothing. You know, once you start thinking like that, you totally misunderstand general relativity. We're talking about space-time. We're talking about a warping of space-time such that, although it has geodesics, the geodesics deviate. We're looking for a mathematical model. It happens to be that curved surfaces have this type of geometry, and I'll explain what that means. When we look at any kind of curved surface, all right, some arbitrarily curved surface, you can go off to infinity, whatever. Let's say you have a bunch of two-dimensional beings living on the surface of this surface. So it's a two-dimensional space, okay? So it's a little bit of abstract, right? Because any two-dimensional surface is going to have some thickness, but we're imagining just a two-dimensional surface of this surface. Two-dimensional beings living on there. Now we have a question. Will these beings discover that they are on a curved surface? Or is there no way to know that the surface is curved if you're only inside the surface? And can they know how much it's curved if they can know that it is curved? For example, when we're standing out here, we see, well, it's curved. We can measure it easily. We measure, let's say, the distance to this bump and the distance to this valley and the distance here. We can construct an exact map, and based on that distance, we can compute the curvature of every point. But if there's a being inside, and it's inside the surface, so it doesn't know if it's crawling like this. It doesn't know that it's bent. To us, it looks bent. But is there any way for it to determine from within? So this was Gauss's invention, and it turns out that you can. And another question that's related is, can one define a straight line on a curved surface? Now, any line that you draw on a curved surface to us is curved. The question is, well, I mean, it depends. If the surface could be curved and have like a valley, and there's a flat valley like this, so this part is a straight line. But basically, you have these curved lines. Can you draw a straight line between any 2 points? So even on this part, right, can you draw a straight line between here and here? Obviously, any line to us is going to be curved. That's not a question. Can you draw a straight line as judged by the beings which live inside the surface? So obviously, we have to have a little bit of a more abstract notion of what straightness is. So we go back to a flat surface, and we look at straight lines, and we figure out what does it mean to have a straight line. And you can do this mathematically. It's called parallel transport. You can read about it on the web. There are many, many, many sources to read about it with nice diagrams. Basically, the way to do it is you take an infinitesimal straight line, which you can define, that you're clear about, and then you make a copy of it, and you paste it alongside it. Halfway, take this, make a copy, right? This line, make a copy of it, but move it up only half of the way so it kind of overlaps. And now you have a line that's a little bit longer. Then take this piece and move it up. That's parallel transport, okay? You can do it more mathematically precisely, of course. When you do that, you end up with a line which has all the characteristic features of straightness, all right? Again, obviously, looking at it from here, it is not straight. But it does have the characteristic features of straightness. All right, any other line drawn between those 2 points will be curved as opposed to this one, which is straight. So this is a more abstract notion of straightness. Again, it's a geodesic. So we say even on a curved surface, there are geodesics. All right, and again, one can define this quantitatively, precisely, and so on. And in order for it to be a geodesic, what has to be is that there is no way to distinguish along this geodesic that it is the geodesic of a curved surface. Okay? That is very, very important. There is no way to distinguish between a geodesic of a curved surface from within the surface and a geodesic of a flat surface like the plane. Okay? So the beings inside, if they're moving along their universe, they will discover the concept of straightness. And individually, they will not know that they are on a curved surface. However, curved surfaces also have the property that from within the surface, if you take 2 neighboring geodesics, and let's say they start out parallel, could be in some region where it's flat, and then it moves to some place where it's not flat, or even infinitesimally in a place which is highly curved, but infinitesimally in the very beginning, they're parallel lines, and they're moving along the surface. As much as they stay straight, they will find their straight lines will deviate from each other. Okay? So individually, this one traveling along this geodesic will find that it is straight, and will not be able to distinguish that straightness from being on a flat surface. And the same for this one. However, when they measure their separation vector, that separation vector will accelerate. And that will enable them to determine that there is curvature. So it turns out that there's all these beautiful properties on just ordinary curved surfaces. One could define geodesity, straightness, and the geodesic line itself does not contain information giving away the fact that there is curvature. It's exactly the same as straight line and flat. Nevertheless, there is relative acceleration of the separation vector. And so the mathematics that describes curved surfaces is exactly the mathematics that one needs to describe gravity. That's amazing. Again, remember, a curved surface is curved. We see it's curved. For the beings who live inside it, there is curvature that they measure. Acceleration of the separation vector. But they don't think of it as a surface in something else, but it is a surface in our universe. Well, we're talking about space-time. We're not talking about space-time embedded in some higher dimensional space or space-time from which you can see that our space-time is curved. That's nonsense. Okay? We're talking about space-time. Space-time has a geometry. As we said before, it has straightness and geodesics for inertia. But this geometry is a warped geometry. And the warping is exactly of the type that we call curvature of surfaces. And so we can use the mathematics of curved surfaces to model gravity. And that's why we say that space-time is curved. And that curvature of space-time produces the phenomena that we associate to gravity. Okay, but it's very important to understand when we say space-time is curved, again, not to think of it as embedded in something else. It's just a warping of the relationship between space and time. Although inertial particles remain inertial, they experience a relative acceleration. how would that translate in terms of a world line? Here you have like a particle and a... So if we look at the world line of this particle and the world line of this particle, or this particle and that particle, right? These two or these two, what will we see? So clearly, the physical separation between them is changing. Now, does separation between particles mean that they're relatively accelerated? No, because you can have particles that are moving like this, both uniformly, right? Both inertial, and the separation between them, here's the separation, here's the separation, here's the separation is getting smaller and smaller and smaller and smaller and smaller, then bigger and bigger and bigger and bigger. But that's just simply the relative motion of two uniformly moving particles. There's nothing unexpected about the fact that the separation changes with time. What would happen if the particles were accelerating, even if they were moving along a straight line? Let's say these particles are not moving uniformly, they're accelerating. What would happen to this separation? If you think about it, you'll see that this separation will not just change, which is a first derivative, it'll have a non-zero second derivative. The separation amount accelerates, so to speak. There's a second derivative of this, not just a first derivative, meaning the separation distance changes in a constant way. This separation will change in a non-constant way. There will be an acceleration of the separation. So we make a vector between them, right? You have these acceleration vectors, and for linearly accelerated particles, they're accelerating in that direction. You have the difference, and you find a second derivative non-vanishing. All right, so that's the way we would notice it in terms of the distance between them. And we can do the same thing for world lines. We can take two inertial world lines, and we look at the spatial, this is the spatial axis, and this is the time axis, and we look at the spatial distance between the two particles at any given time. That gives us the separation between them, the physical separation. And as time goes on, we look at that separation and see what happens to it. If they're, now, what does it mean as time goes on? We have to count time along as the world line the world line is frozen in time. It's space-time. There's no time motion here. We have to impose our own view in the universe. Physics doesn't insert time into the equations directly. It's our own perception. Our conscious awareness of physical events is according to time. We have time evolution equations and so on. Everything is time. But the physics diagrams and the physics equations don't necessarily have time in them a priori. We kind of have to put them in there in order to interpret it to what we are aware of. So we have these world lines. We stick a parameter along them, a time, so that we can march along them and see what happens as time progresses. And we measure the spatial distance between these lines. Now, if they are both inertial, and it doesn't matter if they're moving like this or if they're moving diverging or converging. If they are both inertial, there will be only either no separation change if they're really parallel, or a constant separation change. There will not be an acceleration of the change as we move along the time axis. Okay? So if we want to map what we said is the essence of gravity, that these two inertial particles will experience a relative acceleration, we do have to have two inertial world lines, straight lines, geodesics of spacetime, which have an acceleration of the separation vector between them. Okay, what would that look like on a graph? How would you draw lines which have an acceleration of the separation vector as you move up with some parameters? Like here's the time. Later we'll talk about parameters along world lines and so on. Okay, what would you see? Here we have two inertial particles, geodesic world lines, right? And there's relative acceleration between the particles. Now the first problem is to translate the pictures, because one is a time-based picture where you have particles accelerating, and particle here, they're falling, let's say, and they're accelerating towards each other. So in free fall, you would just see this, they're falling alongside them, and you see these particles, and they're accelerating towards each other. Okay, or they're accelerating away from each other, this way. Okay, as you're falling, you see this kind of motion. What matter does, it has an effect on the medium. Now, we thought of the medium before as space, now we understand the medium as space-time. It has an effect on the medium, space-time. The world line is inertial, and then geodesic world lines, that despite the fact that these are geodesics, there will be this, and we call it deviation of the geodesics. In other words, there will be this relative acceleration of the separation vector between them, which translates, of course, into, if this is a map of space-time, then it translates into relative acceleration of neighboring inertial particles.